All right. Man. Didn't get any questions in advance or any emails, so if you got questions, put them up in the chat. I'm responding to emails this morning as well as kind of like clearing out. I have to start getting ready for summer sometime soon, so I'm starting to like having to clean out everything in my inbox to the sprig. So again, if you got questions, please put them up in the chat menu. I'll try to catch them when I see them. Again, these are not lessons, these are not lectures, these are office hours, so I don't have anything prepared. All right, just asked if I could explain slide 50, so let me bring up slide 50. Under basic conditions, any carbonyl containing alpha hydrogens can be made into a carbon. The most stabilizing carbon can make any more stable electron groups. So, a few things going on here. So let's say we have our alpha carbon here. And this alpha carbon has a hydrogen, and I'm going to consider a few things. So the alpha carbon here, if R was hydrogen, all the R primes are hydrogen, this would still be acidic by sheer merit of the fact that it's resonance stabilized. So the resonance stabilization is what makes it acidic. How do we make it more acidic? So one way to make it more acidic is to convert R here into a carbonyl group. And the reason this creates more stability is now we have two resonance options. We can resonate left or we can resonate right. Also, when we do the tautomerization, we end up generating this really stable six-membered ring. Excuse me. And so that is one way of achieving stabilizations. Another way to make it more stable is to break the CH bond through indirect effects. Sorry. So even if this wasn't a carbonyl, this was just some other group, if R or R prime or R are strongly electronegative, so these are really good at pulling electron density towards themselves. This will inherently start pulling electron density out between the carbons and the hydrogens that make up the alpha carbon. And because they're pulling the electron density away from the carbon hydrogen, they're inherently weakening the CH bond. And that weakening is going to make it more acidic. So the stronger effect here is to put it between two carbonyls, because the two carbonyls, you get resonance. Resonance is always the best way to stabilize a structure. So sandwiching it between carbonyls, this basically creates resonance. Resonance inherently stabilizes the molecule. That said, there are things on the other side of those carbonyls, and if those things on the other side of the carbonyls are really good at pulling away electron density, like oxygens, halogens, nitro groups, sulfide groups, that's also going to increase the acidity of the hydrogen, not because of resonance stability, but because it's pulling off electron density, which is weakening that CH bond and inherently just making it more acidic. All right, the microreaction and Robinson annulation. So this is the hardest part of this test, and it is a lot going on. So you had asked earlier about, like, can I get multiple products from what the key is getting in the discussion in the study packets. And I said, yeah, that was just kind of an oversight on my part because I forgot that the two adjacent, like both alpha carbons can react. And so actually you end up getting this mess of products. The microreaction is kind of the culmination of why these problems with aldehydes and ketones can get so incredibly hard, even for very, very, very simple steps. So the microreaction is going to require, and I'm going to rely heavily, I'm going to go through the slides one by one with you on this because even I'm going to kind of need a little bit of help with this. It's going to require beta diketones. And the reason it's going to need it is that we need to be able to form a stable carbanion, which we can definitely do with this molecule. Now, carbanions will attack pretty much anything that will, it's basically a really super powerful nucleophile. So, go through this slide by slide. As a first step, we can apply alpha beta conjugated alkene alpha beta unsaturated carbonyl compounds. Thank you, notes. Now, what this will engage in is just a nucleophilic attack on this carbon. It'll move the double bond, and this will produce an alcohol on a following workup. And this is just by merit of the fact that it is any carbanion can do it. Basically, this is when you do HX addition across a double bond. The X here is the microreagent, and this is just the 1, 2 or kinetic product from earlier in the semester. So we talked about kinetic versus thermodynamic. This would just be the kinetic product of a diene if instead of having 4 carbons, we had 3 carbons and an oxygen. Now, here's the problem. Oh boy. Okay. Oh, sorry. I said it wrong. Okay. So we'll get an attack here. Basically, we just get HX addition. So this will be the X, and we add it here, and then the H will go to the more substitutable product. So far, so good. Now, the problem is that we now have 2 ketones present. And both of these can be attacked by an alpha carbon. So the initial step of the microreaction is that we basically get HX addition across this double bond. And the X here is the big microreagent. We have the hydrogen here. Now this can attack either of these carbonyls. Now this is symmetric, so it should end up being the same. But if we start counting out, we get 1, 2, 3, 4, 5, 6. So we get a 6-membered ring. So that's carbon 1. Oh dear. 1, 2, 3, 4, 5. That's carbon 6. 6. So by sheer merit of this being an acidic carbon and the fact that we just had these adjacent to the molecule, this can actually undergo a self aldol addition reaction. And so that's kind of the microreaction, is that we kind of get these self reactions when we start the microreaction. So we attack an alpha beta unsaturated carbonyl compound. First round, it just adds to the double bond. Second round, it takes any alpha carbons that are left and causes them to attack on the carbonyls. Now, if we can do it, we end up getting a aldol condensate. So in this case, we have attack here. We get an alcohol. I feel like I counted that wrong. No, I counted that right. So now we can get the aldol condensate. So this will end up, so this is just your aldol addition product. This is your aldol condensate. And instead of just having this simple addition across the double bond, because of what we added, we end up getting this self reaction that ends up forming a saturated, oops, actually no, shouldn't have done that. Should have, oh man, this is so confusing. Oh, because I did it from. Okay, fair enough. Yes, this is really confusing. I think it would have helped if I'd actually taught this in person. Okay, so we do want to form a 6-membered ring. I do know that. So we get the Michael attack. Let's back up. One, two, three. Okay, that was the problem. Was I drew it wrong? Okay, I'm getting there. So this is the first step, HX addition. Next, we're going to want to form a ring. Now, if we have any acidic alpha carbons, it'll form. The big thing here is we're going to focus only on 6-membered rings because they're the most stable. It is possible to do 4-member rings, but we're not going to do it. So I'm sorry, I got this backwards. But there were 2 ketones. Would there be different? Would attack both ketones or just one of them? You would get a mixture of both of them. So this quickly wanders into very complicated territory. So we want to form a 6-membered ring with this being part of the ring. So we have 1, 2, 3, 4. We can go either way with this one, 5 or 6. So if we draw our 6-membered ring, and we start numbering 1, 2, 3, 4, 5, 6. Carbon 1 will be attacked by carbon 6. This will give us the alcohol. So there's the 1,6 bond. Carbon 5 has that on it. Carbon 4 has the branch. And ultimately you would get an aldol condensation that would glad to hear it. I think she's the one asking questions right now. Now, let's say you had an asymmetric. So let's say your Michael reagent was asymmetric and you had this. You would actually end up getting both. So you'd have either listing this is 5,6 or this is 5,6, and so you'd end up with a mixture of products. And so now carbon 6, have a methyl group binding off it, we'd have this one, and we'd have this branch. So for an asymmetric Michael reagent, both of these alpha carbons could attack to give you that 6-membered ring, and you would have to write out both products. So you're going to notice pretty quickly we're going to stick to symmetric Michael reagents just to kind of eliminate the possibility of which one you go with. They're going to end up both reacting. So once we get this self-reaction and we do the aldol condensation, which is just going to be driven by the sheer merit that we can do it, this is the Robinson annulation product. So the Robinson annulation is a self-aldol condensation. The microreaction is just the addition of, okay, so the microreaction is just the addition of this across the double bond. The Robinson annulation can happen if you have alpha carbons within the Michael reagent that can form 6-membered rings with a subsequent alpha beta unsaturated aldehyde or ketone. And then if, goodness sakes, if the R groups here, one of the R groups here is a CO2, that causes it to self-react, any hydroxide that's left over. So the notes aren't very good about this, but to my credit, the book is even worse about this. You form an alcohol, but to trip off the Michael reaction, you actually need a hydroxide. And so the hydroxide is present, it abstracts it, and you end up with this negative charge that keeps floating around in solution. So when you do the first Michael addition, the overall charge in the molecule is a negative. So erase it all out. So let's draw the microreagent again. We're going to have R and R. We're just going to keep it symmetric. So as a first pass, we had to add hydroxide. And this will end up giving us our microreagent. And then we're going to add to the mix an alpha beta unsaturated ketone. Now again, I think we'll see as I start working through the notes. But the thing is, there is a negative charge sitting here. And so when the microreagent attacks, this is going to pull a hydrogen off the water. One, two, three, 1, 2, 3. And to get the hydrogen back on here, we finish with a hydroxide. So with the actually getting the microreagent made, we need the hydroxide, but the thing is that the hydroxide is still there, and hydroxides catalyze these aldol condensation reactants. So what will happen next is that, assuming R here is a CH3 or something that provides us with an alpha carbon, that's going to subsequently attack this hydrogen, give us back water, and now we're primed to do the aldol condensation. So if R here is a CH3 group or has a carbon containing a hydrogen, that's when you get the Robinson annulation. If R is this hydroxide to give you the carboxylic acid, you get a second reaction, which is the decarboxylation. And decarboxylation is just pretty much where you lose a hydrogen or you lose a CO2 group. So you have the hydroxide pulls an electron off, pulls a hydrogen off the carboxylic acid. This will actually kick the bonds around and give you CO2. And then this carbanion subsequently pulls a hydrogen off the water. And now you're back to this product. Oh, thank you for asking this question. It's actually good to be forced to explain the microreaction. So, hopefully that helps. But basically, the microreaction is just generally the addition of some big R group formed by a stabilized dicarbonyl complex. The things that follow get named. So Robinson annulation is when you end up being able to do a self-aldol condensation because there's a methyl group or there's an alpha carbon associated with these. The driving force here being the alpha beta unsaturated ketone, as well as the formation of a six-membered ring. If R here is an OH and you have carboxylic acid, you can get the decarboxylation. The driving force there is that this carbon is pretty acidic, and losing that CO2 will make it more stable. Anything that I would recommend would be helpful. So I think the notes go through, the colors in particular are helping me. So with the reverse synthesis, okay. So I would say break it into steps. So microreaction will always have the general form. So I would do the microreaction first. And the microreaction is just addition to that double bond. And if this is way too much, we'll just say that this is HX. And if I write HX plus this, it's going to be an anti-Markovnikov reaction. So it's going to act anti-Markovnikov because the X group is going to the end of the double bond. This is simply steric hindrance. This has nothing to do with the mechanism so much. And when you finish with the HX addition, X here is just going to be that. And I think the packets do this, that you start by writing out the Michael product. The next thing you need to ask yourself is, what is R? So if R has a hydrogen, then you look at Robinson annulation. If R are both OH groups, you're looking at decarboxylation. So start out with your microreagent, write it as just an X, and do the HX addition across the double bond with the X being on furthest away from that carbonyl, and that's your microproduct. Now, and it's just because I don't have that much space, we're going to erase it. After you do the microreaction, if R is like CH2, CH3, CH, CH3, anything where there's going to be an alpha carbon present, the next thing you're going to do is recognize that it's going to form a six-membered ring. So this is Robinson again. And Robinson is a six-membered ring. So go ahead and start out by writing out your microproduct. And again, we're going to keep this simple. We're only going to stick to symmetric microreagents, so you only end up with one product. Start with one of the alpha carbons and start numbering it. 1, 2, 3, 4. Oops, missing a carbon. 5, 6. Draw your six-membered ring. And just arbitrarily start with a 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Now, this is going to get opened up into an alcohol, so 6 will always contain your alcohol. 1 will always be whatever carbon did the attacking, so this has like a methyl group on it. We'd add a methyl group. And then just start working your way around the ring. So 2 has this branch off of it. 3, 4, 5, 6. So it's like Diels-Alder. When you did Diels-Alder, we did 1, 2, 3, 4, alpha, beta, and then when we drew the product, we look at it as 1, 2, 3, 4, alpha, beta. We're going to do the same thing here with Robinson annulation. That we're going to start with the alpha carbon. We're going to number it 1, 2, 3, 4, 5, 6 until we get to the aldehyde or ketone, and then 6 is going to finish with an alcohol. Let's say that this was this instead of looking like this, it looked like this. We would add our methyl group, and then we would start adding whatever was attached to the respective carbon. So since carbon 2 had this branch hanging off of it, we'll add it here. 3 and 4 didn't have anything on them. 5 doesn't have anything on it. This is what we finish with. Now, for R being a carboxylic acid, again, start with your Michael product. And decarboxylation is actually the easiest one. Take one of your groups and get rid of it. My recommendation would definitely be to number the carbons for the Robinson annulation. My notes try to do that with that numbering, and yeah, you can kind of see, I'm looking at the notes right now on slide 57, like it starts with the alpha carbon is 1, 2, 3, 4, 5, 6, and the OH and whatever's the aldehyde, ketone, and whatever's bound to it, that ends up being on carbon 6, so it ends up producing an alcohol and whatever's off of it. And then carbon 1 is whatever the alpha carbon is. Now, you can get subsequent, and you will get subsequent because you're under basic conditions. You will get subsequent elimination with the Robinson annulation. It's always the alcohol eliminating towards the alpha carbon. Oh, no doubt. I would have 100% say this is the hardest part of the next material. Amines are just memorizing stuff, especially with the naming, it's just memorizing stuff. And phenol is kind of a lot of reactions you've already seen with benzene. The only one with the phenols that you need to kind of learn is the Kolbe-Schmidt. That is kind of a cool reaction. I don't think it's particularly... Well, actually, no. I think it is actually how salicylic acid is manufactured industrially. Yeah, it's been kind of I actually had to like talk and articulate how you do the Robinson annulation. So I actually feel a little bit better now that I've talked about it. Because I can see it, but it's hard to articulate it. All right, so that's it for the live stream. Again, if you have questions, please feel free to ask them either in person or you can ask them in advance by sending emails. And I will see y'all tomorrow.